We just saw how to deal with a single linear function, how to graph it, how to find the slope, the intercepts, that sort of stuff. Now we're going to take a look at solving two linear functions simultaneously, or two linear equations. Okay. To do that, this is called a system of equations. Systems are where we have two or more equations that we're solving together or at a time. And the solutions are going to be the points that solve all of the equations. Now, typically, we're just going to see two equations at a time. And then we're going to look at points or ordered pairs that solve both of them. So here I have an example. The notation is a little bit strange. We list off the two equations and we put one of these, looks like a set brace over on one side to kind of group them together. Okay, so this would be an example of a system of equations. I've got two equations and I want to solve them together simultaneously. Now, to do that, I need all ordered pairs that solve both equations. Now, each equation individually is a set of points, right? An infinite set of points that fills in a line. Well, any point that satisfies both is a point that would be on both lines, the intersection point, okay? Points that are on two different lines are going to be the intersection of the two lines. So there are three common or typical methods for solving systems of equations. We have a graphical method or graphing, substitution, and addition. The substitution and addition are algebraic, whereas the graphical one is where you actually plot them out and look for the intersection point. Now, there are others. There are other techniques. We're not going to talk about other ones. There are some really cool ones actually, but we're going to focus on these three because they're the most applicable and they kind of go along with some of the stuff that we've been talking about. Okay, so for the graphing method, you actually just plot the graph of the two lines and try to identify where the intersection point is. The graphing method works better for some than for others, but we'll go with it for now. So what I want to do is plot these. So if I take the first equation, 3x plus y equals 5, there's two ways to plot this that we've gone over. One is just to find the x and y intercepts and connect them. The other one is to turn this into a slope-intercept form, use the y-intercept and the slope. I'm going to just go ahead and use the intercepts because it's already in standard form, and that's really convenient for finding x and y intercepts. So the x-intercept for this one occurs when the y value is 0. Now, one shortcut is, instead of writing that all out, I just cover up the y term, because if y is 0, that term disappears. And we're left with just 3x equals 5, divide out the 3, and x is 5/3. Now, as a decimal, well, it's really, even as a mixed number, that's 1 2/3 or 1.6 repeated. Okay, so our x-intercept there is at 1.6 repeated, comma 0, or 1 2/3, comma 0. If I want to look for the y-intercept on that one, I'm going to take and cover up the x term, because x is 0, 3 times 0 is 0, and I end up with just y equals 5. Well, that's nice. I don't have to solve that. I don't have my coefficient's already 1. So if y is 5, then my y-intercept is 0, comma 5. All right. So these are my x and y-intercepts for the first equation, and I'm going to go ahead and erase my work on those and just keep those 2 points written up here. 1.6 repeated, 0, and we'll put 0, comma 5 as the other point. Okay, so that's the first line. Second line, negative x plus 2y equals 3. Again, the x-intercept, really, maybe I'll just take this off to the side, save the work here. For the x-intercept on that one, again, I cover up the y value. I get negative x is equal to 3. And so divide out the negative 1, that'll give me x is negative 3. All right, so the x-intercept is going to be at negative 3, comma 0. The y-intercept, again, I'm going to cover up the x term because the x is 0 for a y-intercept. I get 2y equals 3. I divide out the 2. Y is equal to 3/2, which is 1.5, 1.5, okay? So that tells me that the y-intercept is going to be at 0, 1.5. So I've got my x-y intercepts for both graphs. And again, another method or another technique there would have been just to solve these for y, sketch the y-intercept, and use the slope to get other points. But I'm just going to go with this for now. Now to find the graph, I'm just going to plot these 4 points and pair them up and draw the lines through. So on the first one, well, actually, let's get a scale in here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6. I'll go up to like 7 or so. Trying to be consistent here. There's 7 in each direction, good enough. So this is my x-axis, this is my y-axis. The first line, I have a x-intercept at 1.6. Now this is going to be rough, it's not going to be precise. That's the one big downfall to the graphing of these systems, the graphing method, is it lacks precision. So 1 2/3, and then the y-intercept is at 5. It'll be up here. And I plot the graph through those 2 points, try to be as careful as I can be here. All right, so there's my first graph. Second line, x-intercept is at -3, y-intercept is at 1.5. So -3, 0, and 0, 1.5, and I can plot the line through those 2 points. Now again, trying to be careful to keep that pretty close to linear. I think I may have wobbled that just a smidge there where I really didn't want to. Boy, can't seem to get that to draw very straight. Oops. Let's see if I can get that one more time. All right, well anyway, the intersection is in this area right here. And you can see the intersection is the only point that coincides to both lines. So it's the only ordered pair that's going to solve both these equations. And so, close enough. So I want to know what that ordered pair is. Now, I designed this system so that ordered pair is nice. It ends up technically landing on my coordinates of 1. You kind of go down to 1 there and over to 2. Now it might not lie perfectly because I wobbled my graph and the scale's not perfect, but pretty close. So the question is the point 1, 2 a solution? Okay, well it is, I know it is, but we can check it, okay? And to check, basically you run that point through each of these equations and make sure it makes the equations true. So I'll look at the first equation, 3 times the x value of 1 plus the y value of 2. If I simplify that, I'm hoping to get the 5 on the other side. And in fact, I will. I'll get 3 plus 2, which is 5. That equals the 5 on the other side. If I check it on the other equation, I get negative, the x is 1, so it's negative of 1, plus 2 times 2. I'm hoping to get 3 so that it balances out. And in fact, I will. Negative 1 plus 4 is equal to 3, which equals the 3 on the other side. So it checks out on both equations. And so my solution is indeed that point 1, 2. Okay. Now, with systems of equations, we use something called a solution set. We've done a lot of work with set theory and looking at sets before. And so a solution set is the set that contains the solutions. So the solution set is going to be the set containing the point 1, 2. So now we can look at sets that contain points, not just sets that contain numbers. Sets can contain anything. All right. Okay, so that's how I would solve this with graphing. You're actually plotting the graphs, finding the intersection point. And like I said, it's very imprecise. There's a lot of error involved. If that doesn't land exactly on the point 2 comma 1, if that intersection is off, if it's a decimal or a fraction or a really big number, it's going to be really hard to use graphing to solve this. So we have two other methods, and I'm going to, oops, I didn't really want to erase the solution, but I have it up there so it doesn't matter. There are two other methods that we can use, and they're algebraic in nature. So I don't have to sit there and deal with the detail of a graph and making sure that my drawing is really accurate. I can use algebra and get a precise answer. Substitution is given this name because essentially what you do at the intersection point is if you pick an x value anywhere other than that point, the y values for the two functions will be different. But if you pick the x value at that point, the two y values are the same. And so equal x's make equal y's. So what you can do is, because the y's are equal to x's are equal, you can solve one of the equation for a variable, like y, doesn't matter, it could be x, and then substitute that expression into the other equation for that variable. Okay, so now I'm going to go ahead and do that. I'm going to solve one equation for x or y. It doesn't matter, and it doesn't matter which equation, it doesn't matter which variable, but I'll give you a hint. If you can find a variable up here whose coefficient is 1, it's going to be a little bit nicer because you're going to avoid some fractions. So I'm going to choose the y, it's supposed to be an arrow, the y in the first equation, okay, just for simplicity here. So I take 3x plus y equals 5, all right, our first step. I'm going to solve for that y by subtracting the 3x. I'm going to get y equals negative 3x plus 5. Looks like the slope-intercept form. That's good. Now what I'm going to do is I'm going to take this expression, negative 3x plus 5. I know that it equals y in the first equation, so I can replace the y in the second equation with it, because at the intersection point the y's are the same anyway. So I have negative x plus 2 times y equals 3, but that y is no longer a y, it's going to become negative 3x plus 5. So I'm taking the structure from the second equation and I'm replacing the y in it with the expression from the previous equation that we just found, okay? So I'm swapping out the y here with this y and putting what's equal to it. All right, and then I can distribute, so that was our substitution step. Now I can distribute the two, negative x minus 6x plus 10 equals 3. Solve for x is all we're doing here. Combine like terms, I get negative 7x plus 10 equals 3. I'm going to subtract off 10. Negative 7x is equal to negative 7. Well, that's kind of nice. If I divide out the negative 7 on both sides, I'm going to get an x value of 1, okay? Which corresponds, or coincides, no, corresponds is really the word, with the 1 we found before. But I'm not done. I still need the y value. A solution requires both of the x, y in the ordered pair. So I'm going to go back and plug that in, and I can plug it back into either equation. Because it's an intersection point, the y value is going to be the same regardless of which one I choose. So I'm going to go to, I guess it doesn't matter, I'll go to the top one here. So I'll go to 3x, oh, not x, it's 1. I know that x is 1, so it's 3 times 1 plus y equals 5. If I solve that for y, I'll get the other coordinate. So 3 plus y equals 5, subtract the 3, and I get a y value of 2. That's what we were looking for, because that is the solution that we found before. So that just verifies that the 1, 2 solution, and I'll put it in a solution set, is the correct solution that we found before, okay? So that's the substitution idea. Basically, you solve for one equation, you do the substitution here. I'll just put substitute, and then you then you find one of the variables, and then you back substitute to find the other one. So a lot of substituting going on, okay? Hence the name substitution method. Okay, finally, we also have this idea of the addition method. And this one is quite a bit different. And in fact, I'm going to go ahead and finish the addition method in the next video.